Hello, geometry students. How's everyone doing? This is the notes for 10.1, which covers basic definitions and some terminology about circles, and then also some of the property with a few practice problems here. I'm going to go fairly quickly through it. A lot of this, hopefully, you picked up when you're reading through the textbook, and this is just for a little reinforcement and maybe a little bit of practice. But here we go. So let me extend this up a little bit larger. Grab a pen. Okay, so what you see here is just some basic definitions. Most of the ones most people know: center, diameter, radius. Those are pretty normal. A chord, usually people know that, but not everybody. So take a look at that. A chord is just a segment where the two ends are on the circle. We have a secant, where it goes through the circle. You can see that it intersects the circle in more than one spot. It intersects twice. But that's a line, where a chord, it intersects as well in two spots, but it's just a segment. So secant, chord, kind of the same thing, but a secant keeps going. Now tangent's a little different. Tangent just touches the circle in just one spot. That one's very useful. We use that quite a bit. The property that comes up from a tangent, which we're going to see, is that it's perpendicular to the radius. So that can be very, very useful. So a tangent just barely touches the circle in just one spot. You can think of it as kind of like resting on the circle, like the outside of the circle, just barely, like a ruler on top of a cylinder or something, right? And just think of that maybe. But it's just barely touching. The first couple theorems you're looking at here is what I just said. If you have a tangent line, then you will know that that tangent is perpendicular to the radius of or the diameter of the circle, either one, right? It's perpendicular to the radius. And the converses of most of these are true as well. So if you know you have a 90-degree angle up here, then most likely this just touches in one spot and you have yourself a tangent. But usually the way it's read is if you have a tangent, then you immediately know you have a 90-degree angle and it's perpendicular to the radius. The other theorem that we see over here is, now what if we have two tangents? So they just touch the circle in one spot and they have an external intersection point. Then what's true there? And there's a proof that we did for a warm-up to this. So look for the 10.1 proof number 2. It will prove this theorem. And it's also, of course, in the textbook. But it's just saying those distances, RS on the outside, so RS and RT, have to be equal to each other. So if this was 37 inches or whatever, then this would also be 37 inches. Like I said, look at the proof. If that doesn't make any sense to you why that works, or if you can't really visualize it, there's a proof for it, which should have been one of the things you do for this section of the book. Okay, so we're going to use that fact. That comes up quite a bit. This problem here uses that first theorem. It's trying to see if you really do have a tangent or not. So like all our numbers are given to us, all our distances and lengths. We're just trying to determine if this angle up here is 90 degrees. If it is, then I know that this segment up here touches in just one spot and is actually perpendicular and tangent to the circle. So how do I know if I have a 90-degree angle? Well, you use the converse of the Pythagorean theorem. So I'd be taking 12 squared plus 18 squared, figuring out what that number is, taking 6 root 13, squaring that, and coming up with that, and trying to determine if those are equal to each other or not. If they are equal, then we can say we have a right angle. If the hypotenuse side becomes bigger, then we can say we have an obtuse triangle. And if the hypotenuse side is less than those two added together, then I'll have an acute triangle. Let me do my calculations here quickly. The left side, you get 468. On the right side, we will square all of that. And whoops, that was not done right. Just a second. Okay. All right, and that's also 468. Oh, those are equal. So if I know they're equal, then I know this is a right triangle, and I do have a tangent. So I'll just say that, yes, it's tangent. Something similar, when you have these kind of tangent problems, you're always using Pythagorean theorem. So circle A, we can see that's the center. Radius of 8, so that gives me information. It's the radius, not the diameter, so I have to double it for the diameter. BD is 6.5. And they're telling me that this one is tangent. So I'm not trying to find out if it's tangent, I'm using the fact that it already is tangent. So I know this is a 90-degree angle because they told me it was tangent. And I'm looking for CD, so I'll just call that X. All right, so that would just be Pythagorean theorem. 16 squared plus 6.5 squared equals what I'm looking for squared, and you solve. And you should get 17.27. It does say to the nearest tenth, so maybe I should round that to 17.3. These are centimeters. That's my hypotenuse, which is your CD then. This is the external tangents situation. You can see we're given expressions for the sides instead of just numbers straight away. So AD is 2x, BD is 5x plus 12, and my mind is immediately thinking those external tangents have to have the same measure, or the same length. So I know 2x is equal to 5x minus 12 right away. It's given us a little bit of a challenge though, because it's saying, well, here's CD is negative 4x plus 26. And the answer they want is actually, what's this? I'm not going to call it x because I already have an x on my screen and they've already used x in their expression. So just use CB or call it something different like y. And we're trying to figure that out. All right, so we need to get this x first so we have some numbers to work with. So I know these externals, these tangent lines have the same length. So I'll start with that. And solve. So I get x equals 4. I'm going to change colors here so we can see what's going on. So I know if I put 4 in for x here, this will be 8. If I put 4 in down here, this will be 8. Well, that works out because it's supposed to. They're supposed to be the same length. Okay, great. Kind of checks my work. I know the x in the middle is also 4, so that's going to be 10. Right? 26 minus 16 is 10. And so I got 8, I got 10. Oh, this actually makes it nice and easy. Yes, you can do Pythagorean theorem. This is tangent, so you have a perpendicular 90-degree angle. But I recognize this as a Pythagorean triple. This should be 6. 6, 8, 10 is a Pythagorean triple. So that gives me my solution. So maybe I'll just write that somewhere nice. CB equals 6. Very similar problem. This time we're asking whether it's tangent. So converse of the Pythagorean theorem again. Take the two smaller ones. Of course, keep in mind which ones. Which one's the hypotenuse, right? And we're asking ourselves if this is a 90-degree angle or not, right? So that 20 is the hypotenuse. All right, 8 squared plus 13 squared is 233. This obviously is much larger, it's bigger. So actually this is an obtuse triangle, which makes this angle obtuse, makes it big. So in reality, this is still the diameter. It still goes to the center, so I can't really move that. But since I know this is obtuse, it's probably going out this way more in reality, and it would probably cross the circle more than one time if it were to continue out. because it's obtuse, it's not right. And this is a little bit of a challenge. You can see in this unit we start giving you quadratics. We have a squared here and a squared here. Quadratics. So that means factoring, it means quadratic formula, and in order to solve some of these things. We always try to give you a little bit of algebra review as we go through this so that you're ready for Algebra 2 next year. Okay, so this says AD and AB is what they're giving us. We know those are the same because they're tangents. So we just set them equal and solve. Let's subtract. I want to get everything to one side when you're working with quadratics so that this is equal to 0. And then you're trying to factor and say, does this factor? We got 1 and 2. I got 1 and 15. 3 and 5. And looking for combinations that will give me a -1. So I see if I go 2 times 3, that's going to be 6. 1 times 5 is 5. So when I add those together, I'll get a 1 if I subtract them, right? So let me go with x and 2x. I want the 2 times the 3, so the 3 actually goes over here. And I want that to be negative so that I end up with a -6x when I do the FOIL method. And then I want my other number to be a positive, 5, because we need those to multiply out. Let me get a different color so I can point some things out. So when you do the FOIL, this will give me my 2x squared, which is up here. This will give me 5x. This will give me -6x. So when you add those together, 5x and -6x, you'll get your -1x. And then, of course, -3 times 5 is your -15. So I'm just kind of going backwards and distributing to check my work and see I factored it properly. Okay, solutions. What's going to make this 0? Well, if x was 3, it would make this first part 0. And if x was a -5/2, it would make the second part 0 here. So those are my solutions. And that's it. So that's class notes for 10.1. And please watch more videos and do those practice proofs. And read the textbook and compare it to your objective list. And let me know if you got any questions.